Welcome. So today I'm going to take you through an example problem, worked example, where we have a crate which is sliding down a ramp as shown in the figure here. The crate's released from a height of 10 feet, which is where we're looking at the center of its mass to be at a 10-foot height above the ground. We're looking at what is the work done by gravity on the crate, and then what is the change in gravitational potential energy to gain a bit of a understanding of how energy and work are related. So first things first, definition of work. We know that work is equal to a force multiplied by a distance. Now in this case, what we have to remember is that the force and distance must be parallel to one another. They must be moving in the same path. So in this case, what we're looking to do is to find exactly what is the force. Well, the force we know is the force of gravity. Now the force of gravity in this case is the idea that we know that we have a 16-pound crate. So we know that that is the force that is present. The difficult part that we need to look at is what is the path? Well, the path, remember, is along the incline itself. So in this case, the force of gravity is going to be multiplied by the sine of the angle, in this case 60 degrees, because what we want to do is, if we look at this, we recognize that the force of gravity is always acting downward. What we want to do is we want to express the fact that we can split that into a force of gravity that is parallel to the surface and a force of gravity which is perpendicular to the surface. So what we want is we want this force of gravity which is parallel, which is the force of gravity multiplied by the sine of the angle of the incline, which in this case is our 60-degree angle. So with that being said, now we want to know what is the distance that we are moving it along with. So again, let's return to this triangle. And what we have is we've got a vertical portion, which is our opposite side of our triangle. And what we want to know is we want to know what is this hypotenuse length. Because again, we are moving it along the hypotenuse of this triangular incline. And so if we look at this, we can say that this distance would be the hypotenuse length that it slides along. And this is going to be equal to our 10-foot length divided by the sine of 60 degrees. If we take all of this and we now combine that, we can find that we have that work is equal to the force of gravity, which is our 16 pounds, multiplied by the sine of 60 degrees. That is our force term, and we're multiplying that by our distance term, which is our 10 feet, divided by the sine of 60 degrees. Now, lo and behold, the sines of 60 degrees cancel out. We find that we get a work term that is done, which is 160 foot-pounds. So this is our first discussion. What is work done by gravity? If we look at this now from a different approach when it comes to with regard to work and or energy calculations, we're also told that, well, the change in potential energy is equal to a mass times gravity multiplied by a height change. Well, in this situation, what we have is, again, mg, well, mass, m, is equal to our force of gravity, our weight, divided by in this case, because we are working in US customary, we can divide that by 32.2 feet per second squared, which also removes the pounds force to make it pounds mass. But if we go into our equation now, we have everything because height is nothing more than the 10-foot change that we have. So what we find is the change in potential energy is this force of gravity divided by this unit conversion to go from pounds force to pounds mass, 32.2. G, because we're in US customary, is also 32.2. And our height is 10. Now our FG again is 16 pounds of force. 32.2s cancel out. And again, we find that we get 16 multiplied by 10 as everything cancels out. And again, we find 160 foot-pounds as far as change in energy. Now, one part that we do want to look at is, again, a frame of reference. Where are we starting to, where are we changing? Because we are in free fall, or essentially looking at something where we're looking at something like a free fall. The change in height, remember, we want to look at where are we ending compared to where are we starting. So really this height change would be considered a negative height change. We're going downward. Again, depending upon how you're looking at some of these calculations, your instructors may discuss frame of reference, where you may consider something as being positive going downward, negative going upward, all dependent upon the frame of reference and where we place something referred to as a datum line. If we mark this as being our lowest limit, our datum location, therefore our, so to speak, zero location for height change, going above it would mean that we'd have to have positive potential energy. Going below it would have to have negative potential energy. At its location, we'd have zero. So we started from a height where we had positive potential energy, and we lose all of that potential energy, such that now what we can see is the overall change in potential energy is our final potential energy, which was zero, minus our initial potential energy, which is this. So that's one way you can think of this. Also, you can look at it as being a delta H, and delta H, because we went downward, could be treated as a negative. Anyway, we'll look at some more additional examples. Hopefully this stepped you through. As you can see, the change in potential energy and the work gave us the same numerical value, except for, depending upon our frame of reference, a negative sign came in as a result of looking at negative at the potential energy change. Thank you.